Hello, welcome to the stream, guys. So today we are going to build the topmost chip of Nand2Tetris course, which is the computer chip. This is basically, assembly of CPU and memory and ROM chips. So let's see what we have to build exactly. CPU. So we have already created a CPU chip, and this is what we have to build. This is the computer diagram. Where is it exactly? Keyboard, memory implementation, hack computer. Yeah, so this is what we have to create inside the HDL file. We already have a CPU and memory chip, and I guess we also have RAM 32K. Although we didn't build it, I think it is already inside the built-in chips. So check it out. Tools, built-in chips. Yeah, here it is, ROM 32K. So we are going to use this built-in chip. Yeah, in fact we are going to use all the built-in chips anyway. Even though we created CPU and memory chips by ourselves, we are going to use this built-in chips because they are optimized, and we just built it for just the heck of it. So what's more, yeah, so this is the hierarchy of all the chip parts. So we started from this basic elementary logic gates, and we built adders and registers and RAM units. Yeah, so for the project 1 section we built this logic gates, and in project 2 we built adders and ALU, and inside project 3 we built these registers, RAM chips and PC. And yesterday we built CPU, and before that we built this memory chip, which is from the project 5 section. And finally we are going to build this, the topmost chip, which is the computer. Which is just an assembly of this two chips, not two, three chips, but ROM 32K is basically a memory, so that's that. Okay, this is the implementation that we have to satisfy inside the HDL file. So let me open up the HDL file first of all. It's this one, computer. Wait, we have a lot of computer chips. Which one we should be using? I guess it is this one, the simple computer.hdl. Okay, so inside computer we only have one input, so that simplifies it, I guess. We only have one input, which is reset. So what is the reset bit do? Basically, when it is set to 0, the program stored in the computer's ROM executes, and when it is 1, the execution of the program restarts. All right, and how do we control this reset? So this reset we can directly input it to the CPU, but if I recall correctly, this reset was let me see, when we applied this reset bit to CPU, what was it doing? This is the implementation of CPU. Yeah, it is over here. So signals whether to restart the current program or continue executing the program. Yeah, and in this case, in case of CPU, we directly applied this reset bit to the program counter, I guess. Let me open up the implementation of CPU. Nand2Tetris projects quick section. CPU implementation. CPU.hdl. So where did we apply reset? Yeah, so we directly pass this reset bit to program counter. Cool. So when reset bit is set, it will clear the value of program counter and set it to 0. So that will restart the program. Awesome. So yeah, let's get the CPU chip and ROM 32K and a memory chip. We just have to glue together these 3 chips. So I guess there won't be so much of logic, I guess. So first let's get the CPU chip. CPU. But before that we have to check the implementation of CPU because it contains 3 input and 4 outputs. So for that, first for the input, let me open up the implementation in this slide for the reference. Yeah, it is over here. So for the input part, wait, if we are using the CPU chip inside computer and we don't even have this inputs, then okay, right, so this inputs are going to come from the, wait, so this input m, let me first write it down. Input m, this input m is the value of RAM A, so this will come from the RAM chip. So before I pass the inputs, let me just write them down and we will try to figure out what to pass it later on. For the reset bit, we can directly pass this reset bit which we are given. So, and after that, let's write the outputs. Again, for the outputs, we are not going to pass anything right now. Write m, then we have address m and program counter. Okay, that's it for CPU. Now we need a memory chip as well. Memory. Now we have already built our memory chip as well. So let's check the implementation so that we can write the inputs and outputs. And where is the memory? Memory implementation. Yeah, it's this one. So in case of our memory chip, we just have an input address and an output. Now we also need a ROM 32K. So let's check the implementation of ROM 32K in this window. ROM, it should be inside. Where are we? We are inside 5th folder. So we have to do the built-in chips. ROM 32K HDL. So this is the interface of ROM 32K. We just have one input and one output. Input is address and output is just out. So not that complicated. ROM 32K. ROM 32K. We have address as the input and output. Okay, so now we have got these three parts. Let's figure out what we have to pass as the inputs and outputs. So now this the ROM 32K will have the program, the hack program, and to start the program, what we have to do, to run a program, first we have to load the program into the instruction memory. Okay, yeah, load a program into instruction memory. How? Yeah, that's a question we don't have to worry about right now, because I guess this HDL test script will already load the program. So we just have to figure out how to start it. Press reset. Okay, so after we press the reset, this will so let's see, the test script will also pass the reset bit, and that means that it will set the program counter to 0, and after that it should start, the program should start running. So how is it going to start running? Yeah, this is the interface of ROM 32K. From the, we have this address which is coming from the PC output from the CPU. So this PC output, we will be passing it to address. So for that, I guess I have to keep it inside an intermediate variable. So what are we going to call it? ROM add. Yeah, that will be apt. ROM add for ROM address. And let me see, this ROM address is of 14 bits, and this program counter, this PC should be of 14 bits as well. That way we won't have to figure out which bits to pass. Where is it? Yeah, it is over here, but yeah, it is of 15 bits. So yeah, that means we have to get rid of one bit. Now which bit we are going to get rid of? You see, now this is the thing which I always forget about. I will have to check the implementation of my previous is it? Computer CPU HDL. So in case of PC, we are passing, where is it? We are passing 0 to 14 bits, and these are coming from the output of what? So okay, output of program counter. We're just passing 0 to 14. That means we are passing 15 bits. So we are passing 15 bits in total to program counter, but in case of ROM, where is it? ROM. So in case of ROM, we just have to pass 14 bits. Why only 14 bits? 16-bit 32K chip. So I guess it is of 32K RAM. So 14-bit address is sufficient, I guess. So yeah, we'll get rid of this 14 bits. It's alright. So to do that, we first have to select these bits. 0 to, I'm going to get rid of 14 bits. Now we can pass this ROM add to this address. That will give us the input for ROM 32K. For the output to the CPU's instruction. So now this output will go inside this instruction. And this instruction is of 16 bits. And if I recall correctly, this instruction input is of 16 bits as well, because this is basically the the instruction bits. It is either of type A or C. So let me just, yeah, it is also of 16 bits, so we can directly type it. Inst, yes. And now we are going to pass this inst over here. So you see, we are just gluing together this different inputs and outputs. The only thing which is coming from outside is this reset bit. Now, so we have taken care of this ROM 32K chip. Now let's see what we have to do with this memory chip. The memory chip takes one input and it takes two inputs, and I guess this input is the value which we are going to, yeah, it is basically a value, and this address is the address of this particular register inside the memory chip. And output will get either the output from that address or this input, yeah, whatever. So where is it? Memory. Input is of 16 bits, output 16 bits, and address 15 bits. This input is a value, output is a value, and address is address. Now this must be coming from one of this, some of this outputs of the CPU. So let's see which outputs we have to plug it in. Yeah, these are the outputs: output M, out M, address M, and write M. So I guess this address M is for this address, and write M must be this out in M. gonna open this in another video, not another video, another tab, so that I can compare it. I think this is not going to work. Let's keep it inside two tabs anyway. So in this tab, I'm going to open the CPU interface. So this is the CPU interface. We have output M, write value to write into M. Okay, so, and it is of 16 bits. And if I open up the memory, input, so this output M is the value which we have to write inside this RAM. What the heck is this bit for? Write M. This is for the address of RAM, so I guess address M, which is of 15 bits. So this address will come directly from this address M, and they are both of 15 bits, so we don't have to worry about getting rid of any bits. Okay, so let me first of all write this output M bit to the memory. Well, you know what, I can directly write it to the same variable of same name. It is perfectly all right. Value to write into RAM. So and now I can pass output M over here. And we could have done the same thing with this instruction as well. So, yes. This is perfectly all right. And I guess for the address, I'm not going to write inside address because we have address variable inside all of these three chips, so let's not confuse ourselves. This is all right, RAM address. So after that, I have got this output M and I'm passing it to this memory. Okay, cool. Now after that, I have to pass this address M to this address. Yeah, where is it? Address. Yeah, we'll call it address M. Address for the memory. Now I can pass this address to this RAM. Okay, now also have to pass this output. This output gives us a value, and we can pass this output to this input the value of RAM. Yeah, we are reading the value which we are reading from the RAM input AM. So I will pass it to input AM, and let's just recheck if so this enam is of 16 bits and the value which we are getting is of 16 bits as well. So yeah, we can directly pass it to the variable. Now we can get input AM here. Right, we have taken care of this memory chip as well. Now what is remaining? Wait, yeah, what is this? Write M for write M, write into memory. Now what are we passing to this right hand? I will have to check the implementation. Yeah, just over here we are passing this third bit of instruction. What is the third bit? If I recall correctly, they were for the destination, I guess, inside the instructions. Yeah, it was inside this slide. Yeah, so third bit is this one. No, it is this one, destination bit. D1, D2 and D3. Now what does this D3 bit represent? It is 1 whenever we have M. We have to write to or read from M, or write to, not read, just write to. So that means what do we have to do with this write M? Because we don't have wait, I get it. Are we missing any input inside memory chip? See, here we have three inputs and one output, but we have only used two inputs. So are we missing any input to the memory? That is the diagram of memory. Yeah, we are missing this load bit. So let's write the load bit. Load bit, and now we can pass this write M bit to load. So I think this is it for this computer chip. There's nothing more we can do. So I guess let me try to load it inside the simulator. CPU, not CPU, computer. Because it is going to give us error. It is 15 and different bus widths. Where? Address and room address. Okay. Where is room though? The room is a 14 bits, right? Okay, pause. And how many bits are we passing to this ROM? 0 to 13 bits. Passing 14 bits. Then why is it complaining? Okay, we are passing 14 bits, but we have to pass 15 bits. Okay, so I guess there's a typo in this figure. This address is of 15 bits, but they have written it is of 14 bits. So that means we don't have to select individual. We can get rid of this thing. Let's see if it works now. Cool, so it is not complaining now. So let me load the test script as well. Where is the test script? Computer dot. Oh wait, I think we don't have a test script for this chip. Where are the instruction? Test by running some hack programs on the constructed chip. Okay, so it seems we have to manually check if we have a working computer chip or not. For that, what we have to do? First load the computer HDL. So after that we have to load a program. This program must be inside. Yeah, there were many files inside this folder, so let's see if we have program. Yeah, we do have add.hack. So let me load this inside the ROM. So now we have a program inside the ROM. Now what can we do with that? Maybe I should start running the program. So yeah, let me start to run it. Adds to constatize the result to RAM. Wait. That I haven't passed any input to this, so first I have to pass the input. Let me stop it and reset it. Okay, yes, clear the program. I clear the RAM as well. What the heck? It is just loading. I will be back in a minute, guys. Hello. हाँ हाँ बोल हाँ हाँ પણ ક્યારે છે એવું કેટલા વાગે ના હું તો બીજે રહું ગાના સાહેબ બીજ જોડે હશે ને પણ એનું ક્રીસ જોડે હશે કદાચ It's still loading. Let me reload the chip. So now let me load the add program again. So what is assembly? Yes. What does it do? It adds two constant. Okay, so we don't have to provide the input. It is just adding 2 and 3 constants. It's constant. So first it is loading 2 inside the address and storing it inside the D register, and now it is saving this 3 inside A, and after that it does D plus A, which does 2 plus 3 and storing inside D, and after that it is selecting the memory, this 0, to selecting it is storing the D at that point. So we should, after this program is done running, we should have 2 plus 3, which is 5 over here. So let's see if it does that or not. Because we are not getting 5, but we are only getting 3. So I think there is a bug. Ideally we should be getting 5 inside this RAM 0. So I guess we have to step one by one to it. So let's step one by one through the program. Okay, I'm selecting 3 instruction register 3 address M2. So by the way, why is this D 0 only? It should contain this 2. Let me reset it again. Okay, so let me start clocking it. 2, Okay, so if I clock it again and again, it is just running the wrong. Maybe I'm just trying to run it in a wrong manner. So test the computer chip is to have execute some sample program. So first load the computer.htl chip. You can write a test script that loads the computer.htl file chip description into the supplied hardware simulator. So I have already loaded it. After that, loads a machine level program from an external .hack file. Yeah, I have done that as well. Now run the clock enough to execute the loaded instruction. Add 2. Okay, I have 2 inside A. Why do I have 3 inside D now? Should have. Does that mean I have incorrectly applied the inputs? Let me try to reload the program again. Okay, so the reset is 0. That means if I try clocking it, it will start from this instruction. Now A is 0, D is 0, PC is 0. But we will have 2 inside instruction 16. And I guess it is because we have selected this thing. Okay, so now if I clock it on, I have A2. Okay, now the program counter should increment. Wait, it jumped from 0 to 2. Why did that happen? Okay, totally skipped this instruction. So wait, this program counter jumped to 2. Why did that happen? This program counter. Wait, this program counter jump to 2. What does that mean? That means we loaded 2 inside this head. Okay, and this 2 came from A. Because A was 2, we loaded 2. And the wait, what have I done wrong? This program counter should be 1, right? So it should have been incremented, but it jumped to the second instruction and we totally skipped this instruction. That means it was loading the value of A inside program counter, but it should not load the value because I'm not jumping anywhere. So why did that happen? What are the states of this address M15? Address M is the memory. Okay, ROM address is this one. And this ROM address is coming from, where is it coming from? What the heck is, oh, I see. So this is the input. Where is ROM address? There's no ROM address, I guess. Yeah, it is over here. So I'm taking the input from PC and passing it to the address. That is correct. Taking the value of program count. So what does that mean? ROM address 2. So this control bit of ROM of the program counter is not being taken care of correctly. Did we pass to this program counter control bit? PC load. There's a lot we did to pass the control bit to program counter. It's a combination of bunch of instruction, jump and so that means it is telling our program counter that it's time to jump, but what tells our program counter it is time to jump? If I I can add this test script as well. So let me reload it again. Is it computer add and computer add compare? Okay, so let me try to run it now. Okay, so it seems we have a problem. What's the problem? Time yarn, reset bit is 0, A register is 2. Okay, so we are storing 2 inside the A. D is 0, PC is 0, RAM 16 is 0, RAM 16 1 and 2. Okay, the program counter has not been incremented. So that's the problem. Why did it not work? Why wasn't it not incremented? Where must be the problem? See the program counter. The incrementation of program counter depends on PC Inc. This PC Inc comes from well, in this case it is our own implementation, but input is a register O. So I must see there's a problem with program counter. But that can be a problem because these are coming from the built-in chips. The CPU and memories from the built-in chips. So the only problem is that we might be passing the incorrect inputs to the CPU. So let me retrace it. So the jump bits or the incrementer of the wait, there actually might be a problem with the implementation of built-in chip as well. I don't know. But if there was a bug in the implementation of built-in chip, someone might have reported it already. So I don't think that is the case. So what does that mean? So the control bits of program counter depends upon the instruction bits. Now not the whole of the instruction bit. I'm just well, in our case we have an A instruction. So in case of A instruction, we don't have to do anything to the program counter, we just have to increment it. There's no loading happening. I think I might have to go through it step by step. Loading the add.hack. Instruction is 2 because we are loading 2 inside the A address register. Now what happened? This address M is getting 2. Address M, what is address M? Address in the data memory. Yeah, so that's alright because we have selected it at A. But in this case we should have, well, let's see, where is PC? Where is PC anyway in this thing? Don't have a PC output. Whoa. So we have input M instruction and output M, write M, address M, and room address. So this room address is PC. All right, I think I know. It is still 0. So now we can. So instead of roam address, I can store it inside PC. That will be easier to debug. PC. Okay, now let's reload it again. the test script of add. So now we have PC. So by step, the species should be getting 1. Now to this PC to be 1, what needs to happen? Does any of this inputs have to change? What is right hand? This is for the load instruction of the memory. So yeah, that's not what. And this input m is wait, what is this input m? Input m. M. It's an input from the memory. Yes. We have this instruction, which is coming from the room. We have reset bit and output m. It is writing to the memory and address m. This one, address of the memory, and the program counter. Wait, do I have to clock it? Okay, so not only have to run the program, I have to clock it as well. Wait, what is happening? So this program counter skips 1 and directly loads 2. But after that, it correctly increments the program counter. So, it seems harder to debug this because I don't actually know where the bug is. If it is inside my HDL file, basically my implementation, or the test script, or maybe I'm running the test script incorrectly, or maybe there's no, I have not loaded something. So the problem might lie anywhere. Why is it failing? So as per this diagram, we have CPU. Input M comes from the output of memory. This is correct. And this instruction comes from, well, from the output of RAM 32K. And this reset bit is coming from this reset bit from outside this chip. And we are writing this output M to output M, which goes to the memory as the input. And we are writing the address M to this address of memory. And this write M goes to the load bit, and we have this program counter which is going back to the address of this ROM 32K. So it seems as per the diagram we have a correct implementation. Let's see if they have given any hints. Maybe I'm just trying to test it incorrectly. Okay, wait. So does that mean we are not using the built-in chips? So now if I try to load this CPU chip, okay, wait. This PC incrementer is in my implementation, it is 1. In my implementing, it is basically the inverse of PC load. So if PC load is 1, then this PC incrementer will be 0. I might know what must be happening. So maybe this computer chip is not using the built-in CPU chip. It must be using our own, the implementation that I created of the CPU. And there might be a bug in my implementation of CPU. But when I tried to load this, so let me try to test it again using the CPU test. So yesterday it was running correctly. Okay, wait. So I guess did not run this time. Why? Yesterday it was running correctly. Let me try to reload it again. CPU. Hey, maybe I load incorrect. Wait. Alright, so it seems my implementation is not working, but why was it running yesterday then? Let's see. What the heck? Did I change the program or something yesterday? Because yesterday it was working correctly. What the heck? How can that be possible? Time 0 instruction is this A, reset is 0, output is 0, right time is I can't even scroll this. What the heck am I going to know? What is outside of this window? Loading the instruction. So the instruction is should have the binary form. This is the instruction. Instruction is of type A. That means right hand. Let me open up. Less CPU dot tst dot compare. So this is the compare script. Okay, it's this much only. This is the output. So if we compare it, this right AM, it should be 0, but we are getting 1. Okay, so that might be causing problem. And this right AM is coming from, let's see, from instruction with 3. 0, 1, 2, and 3. Okay, I see now. This is of type A. This instruction is of type A. Now in that case, we don't have to pass this. It doesn't mean anything. This bit doesn't mean anything if the instruction is of type A. So what do we have to pass to this right hand in case of A instruction. Is this right hand again? That's it. Implementation. Okay. Right hand is the right load bit of the memory. Now in case of M, or in case of A type instruction, A type instruction is basically just select changing the A register. We have to pass to right hand. Then in case of A type instruction, we are not changing. So let me check the instruction bits first. We're passing this 0, 1, 2 and 3, D3. So this is for the destination. In computation, we are selecting the destination, but in case of A type instruction, we are not necessarily changing the state of the memory, right? We are just changing A register. So right, that means we have to pass 0 to this right hand when the instruction is of type A. So I guess what I can do, instead of passing true, I can pass instruction. So we know if it is a type C instruction, if this bit is 0, sorry, if this bit is 1, then we know it is a type C instruction. So if I pass this is of 16 bits, so if I pass 15 bit, so let's see, this instruction 15 bit will be 0 for A type and 1 for C type. So if it is 1, then we will have whatever is inside this instruction bit 3 inside right hand. But if it is 0, then it doesn't matter what we have inside 3, we will have 0 inside right hand. So yeah, I think this might work. So let's try to do. I wonder why this program worked yesterday. CPU. So try to run it. Okay, so this time it is running, but we have an issue at this. Then what the hell did I did yesterday? It is running. It was running. What's the issue now? This is the output. For this line 7. Oops, it seems our program counter jumped to 1003. Why did that happen? It should just increment it. Because this PC load was 1. And why was it 1? Okay, so now that means oh, this PC load is 1. It is an instruction of type 0, A type instruction. A type instruction. Okay, let's see. A type instruction, we are just loading the so let's see. This PC load should be 0 in this case, but it is not, and it is not, therefore it is passing this value of A register, which is 1003, to the program counter. Why isn't it set to 0? Because what kind of logic have we used for this program counter load bit? It's a function of J1, J2 and J3 bits and the jump bits JGT. But what if the instruction is of type A? This is for when instruction is of type C. If it is of type A, what guys, I will do it later. I'm going to have a break right now for the lunch. Alright, guys, I'm back. So, where was I? So, just like we did for this write time instruction, when the instruction is of type A, let me lower the volume. Okay, so when the instruction is of type A, we don't want to set this PC load bit as 1. So in that case, it should be 0, because we are not loading anything inside the program counter when we are just running the A type instruction. So for that, what I'm going to do is, let's see, I'm going to call this as PC load 1, and now I'm going to get one AND instruction, and for the A input I will get PC load 1, and B instruction will be the instruction bit 15, which contains the opcode. Okay, so after that I'll pass the output into PC load. So what this will do is, if this instruction bit is 0, then this PC load will remain 0 regardless of this PC load 1 input. But if this instruction bit is 1, that means the instruction is of type C. That means in that case this PC load will reflect this A variable. Okay, so let's try to run it now. CPU. I wonder how did I miss this bug yesterday, even though I loaded the same test script. I might have to recheck the stream again to see what was I doing yesterday. Awesome, so that means it has been fixed now. Let's see if it runs all the way. Awesome. So wait, so what the heck did I do yesterday? This can't. Let's check the yesterday's video to see what I exactly do. Was this one? Where's the yesterday's video? CPU. Oh. Streamed a 1 day ago stream. Why is this one showing before this one? The order is all messed up. So yeah, this was what I did yesterday. So yeah, I'm loading the same HDL file and basically I'm debugging it. What happens afterwards? I want to skip to the part where the script ran perfectly. Oh wait, I think that's the problem. I loaded the memory.txt. Let me show you. Okay, so I'm clicking on this button and I loaded this memory.txt. So that's why it ran successfully. Damn, that's what I did wrong yesterday. Okay, it doesn't matter. Today we have successfully created it. So I think as I was thinking, this implementation of computer is using our own implementation of CPU. So let me try to load this computer on again. First we will have to load the program. Where is it? Projects add.hack. Now we are going to load the test script of computer add.txt. Now file, let it run. Awesome. So I guess this time it is running perfectly right. So that means this chip is using our own implementation of CPU and memory. It is not using the built-in version. And you see this time it is incrementing the program counter. Wait, this is the compare script. This is the output script. So it is incrementing the program counter correctly this time. Awesome. Let's try to load different program file inside ROM. This time let's load max.hack. What does this program do? Max.hack computes the maximum of RAM 0 and RAM 1 and writes the result in RAM 2. Okay, it doesn't matter. We'll have to load. So yeah, I think I loaded it. So now let me load the test script for this max.hack. Okay, what does it do? It gives the result in RAM 2. First we are loading 3 inside RAM 0 and 5 inside RAM 1. So 3, 5 is 15. That means we should be having the result inside RAM 2. Okay, let it run then. it is not multiplying, it is getting the maximum. Okay, RAM 0 and RAM 1, maximum out of RAM 0 and RAM 1. So RAM 0 is this value and RAM 1 is this, so the maximum is this value. So this program is working correctly as well. And now this time let's load the third program, which is drawing a rectangle. Let me reload it again. I think I messed up. Rectangle.hack. Okay, now what do we have to do? Yeah, load the test script of rectangle. I think we should open up the screen. Should display a rectangle, right? A rectangle should be drawn at the top left of the screen. Okay, so this program is not working. What's the issue? At the third step we have 23034000. This should be 4 instead of 0. Deregister. Okay, deregister is not getting 4. Okay, why is that happening? First we are loading 0 inside the A register, then we are storing okay, whatever A is pointing at. So this 4 value inside data register. After that we are storing 23 inside A and D jump if less than or equal to. So if the destination, if the D is less than or equal to 0, but wait, D is 0 when it should be 4. So I think we have to run it step by step. So let me reload the program. Nand2Tetris projects 4, not 4, 5, rectangle.hack. So let's step through it one by one. Let's also load the test script. What is this going to do? First we will load the rec.hack inside the ROM. After that it will set RAM 0 to 4 and it will clock basically. So let me open the screen assembly. So if I step one by one, first it should load 0 inside A. What the heck happened? D is equal to, yeah, now at this point this D should contain 4, which is, yeah, we are getting 4 inside D. But after this, okay, but after this instruction, this value is being overwritten. So that means we have a bug, guys. We have a bug inside, let's see, D register, where we are loading the value of D register. It is happening over here. We're getting the value from ALU 0, which is what? The output of ALU. Okay, I guess, yeah, this is the same bug, I guess. Here we don't have to load this read register if the instruction is of type A. So yeah, the same bug. That means the solution is same. I'm just going to copy this AND gate here. So what we are going to do, we're going to pass ALU output over here, and again this instruction bit 0. So if it is 0, this will be 0, and we'll call this dreg L. dreg L. So let me try to reload it again. Computer.html. What the heck? Okay. Yeah. Yeah, this should be instruction bit. This should not be ALU. This should be, yeah, this was correct. Oh wait, I forgot now which instruction bit we have to pass this. Fourth bit. So this should be fourth bit. Now it is not going to complain. I missed a semicolon, but where? Oh, not semicolon, I missed a comma. Okay, let's load. Wait, what do we have to load? Yeah. Load this program rectangle. So let's let it run. Okay, there's a line appearing. But this program should draw a rectangle. So yeah, it is going to uh, create or display a filled rectangle, not an empty one. So it's drawing it line by line. Okay, so we have a small rectangle, the top left, and the script has run successfully as well. So even though we had bugs in this program, I'm assuming that after running this three scripts, it has tested all the different inputs our program will be having, and our implementation is correct. I'm just assuming because I missed this, I missed the, I basically assumed that we are just having a C type instruction. For A register, I already implemented the logic. And in A register case, I used the OR gate. Why did I use the OR? Am I using not OP anywhere else? No, just using it 2 times. So this OP is basically if this instruction bit is 0, this not OP will have 1. So I am passing 1 over here, and A register L will reflect this instruction bit 5th. What is inside 5th? Fifth is 0, 1, 2, 3, 4, and 5. Yeah, this bit represents whether we should load the value inside the A register or not. And I am using an OR gate. Why? So for the, if this thing is 1, okay, wait, I might have a problem. Wait, no, maybe not, because if this bit is 1, then the instruction is of type A, so we are going to load inside A register anyway. But what if it is of type C and we do need to load it inside A register? Yeah, I think we might have another bug. So if the instruction is of type C, it means this not op will have 0 inside it. But this will have 1. So, yeah, it has been taken care of like that. We could have just used the AND gate as well, right? What if we had used AND gate like this solution and pass the instruction bit 5th and op as the B? No, I think AND gate might not have worked. Yeah, let's keep it like this only because it is correct. Right, so it seems we have completed the projects of project section 5 as well. We don't have any more projects inside this section. And in the next section, what do we have to build? Assembler. Do we have to build an assembler? Wait, these are the test programs. Write an assembler program that translates program written in the symbolic hack assembly language into binary code that can execute on the hardware platform. Okay, so we'll have to build this assembler in the next project, but before that I will have to review this fifth week, no, the sixth week videos. I will have to watch this videos. After that we'll get started with implementing the project. So I guess there's nothing else we have to do right now. So I'm going to end this stream now. I will see you guys in the next stream. Bye bye.